Good day, everyone. I am Abhishek, and today I am going to be talking about the evolution of traffic routing in a streaming world. To share a little about me, I am a computer engineering graduate from Purdue University. While in college, I interned at Bloomberg and Microsoft for a summer each. For a little over 3 years now, I have been working as a software engineer at Facebook on a team called RTI. RTI is short for real time infrastructure. We are a team at Facebook that enable live, real time, interactive experiences across most of the products you know in the Facebook family. A couple of super familiar examples that our team powers would be the comments and reactions that float by on live streams on Instagram and Facebook, or the typing indicator on your Messenger app. In this talk, I will use the evolution of my team's architecture through three different stages to share with you the learnings and wins we observe. These will include topics such as rendezvous hashing, heat distribution, sticky routing, virtual isolations, and more. Let me first set stage with a 5,000-foot view of our initial architecture. Here we see that each device subscribes to a few streams of data. Every stream then arrives at the gateway service, which is tasked with user authorization and traffic routing. The stream then gets routed to Nexus. Nexus is a service that manages these streams and serves them with real-time data as part of RTI's publish-subscribe infrastructure. Nexus itself communicates with the global key value store for updates. In this talk, we will focus on infrastructure that falls within the highlighted area. Zooming into a single region, we have many hosts present, each depicted by a dashed green box. Each host serves multiple gateway tasks and a single Nexus task. All of the gateways on a host talk to the Nexus on the same host. This is what I call a co-located architecture, since multiple services are co-located onto a single machine. Now, the co-located architecture has a bunch of issues. Both services have to share resources and deal with independent deployments and common dependencies. Also, the overall architecture has a low fault tolerance. To illustrate this point, let us say that Nexus on host 1 is unavailable. This would effectively mean that all the streams attached to all the gateways on that host can't be served. For streaming traffic, this is even worse since those streams are going to stay for a long time, hoping the Nexus would come back. All of these changes and more led us to building the off-box architecture. In the off-box architecture, Nexus was separated into its own fleet with a host per Nexus, and each gateway connected to more than just a single Nexus. The dependency of multiple gateways to a single Nexus was finally broken. With the off-box architecture, we were able to isolate customer traffic, be more fault-tolerant, and dynamically load balance. Since moving off-box, each gateway could connect to multiple Nexuses. This allowed us to move certain unpredictable and spiky customers into their own isolation, that in turn helped protect other more predictable customers from a noisy neighbor problem. Moving off-box also improved the total fault tolerance of the system. Say one Nexus became unavailable. The gateways could now reroute affected streams to the other Nexuses. Affected gateways would also connect to a new Nexus so as to maintain the ideal number of connections for better load balancing. This leads us nicely into dynamic load balancing. Let us look at this one single gateway here. We observe that one of its Nexuses is starting to get hot. Knowing this, the gateway will redistribute load elsewhere, easing load on the hot Nexus. This dynamic reaction gives space for the hot Nexus to cool down. Finally, when all is back to normal, the gateway can accordingly rebalance load across its connected Nexuses. Now, one major challenge we observed was that Nexus was not built to support the handling of a massive number of gateway connections. A full mesh connection where every gateway G connected to every Nexus N would result in every Nexus maintaining G connections. However, if each gateway connected to only K Nexuses, each Nexus would only have to serve G times K over N connections. We realized that K is equal to 3 worked best for our Nexuses. This led to a new question. Which K Nexuses does each gateway talk to, given one gateway doesn't know about another's decision, and we want to evenly distribute the connections? Additionally, a Nexus could come up or go away, and we want to minimal disruption around these events. To appreciate the complexity of this problem, let us run through a very naive solution where each gateway picks 3 random Nexus hosts to route to. At startup, everything looks good and random allocation is providing a good distribution of connections to each Nexus. Now let us say a Nexus becomes unavailable. Gateways connected to it lose that connection. Affected gateways now randomly pick a new Nexus to talk to. While initial state looked good, we have already degraded to a state that is less evenly distributed. Now let us say that Nexus is available again. There is no gateway that will redistribute since they are already connected to 3 hosts. This results in the deployed nexus now being unused. From this example, it is clear that we need a more sophisticated solution to this problem. So what do we want? Given that each gateway has to independently make a decision, we want to see an even distribution of connections with minimal disruptions when the fleet sees a change. A good solution to these requirements is rendezvous hashing. Rendezvous hashing is an algorithm that allows clients to achieve distributed agreement on a set of k options out of a possible set of n options. This is exactly the same problem statement we set up just now. We too want every gateway to pick k out of a total n nexuses they would connect to. And so each gateway will run this algorithm independently. On each gateway, a weight for every available nexus is computed. This weight is the result of a hash of the gateway running the computation and the nexus in consideration. Here, under each nexus, we see the weights for that nexus as computed by gateway 1. Nexus 1 has a weight of 78, Nexus 2 has a weight of 13, and so on. All of these weights are sorted, and k weights with the largest values are then used to identify the nexuses to connect to. As expected, we can see gateway 1 connecting to the nexuses with the top k weights. Since the gateway is part of the hash, each gateway will pick different nexuses to connect to. As an example, if we look at another gateway, the resulting weights are different, and so we see that it ends up connecting to a different set of nexuses. For rendezvous hashing, a non-cryptographic general-purpose hash should be used. Murmur hash is one such commonly used hash. That said, any other hash function with good distribution would work just fine. As with all hashes, a very small fleet size will result in distributions looking a little more uneven than desired, as all these hashes work best at scale. If you remember, we had also called out for minimal disruption as a requirement. At the bottom, we have a table with the weights of each nexus by gateway number. Currently, every gateway is connected to its top 3 nexuses, and we have good distribution. Now let us say a new nexus spins up as the fleet of nexuses got a new capacity added. Each gateway will then recompute hashes. It is worth noting that since hashes are deterministic, existing hash values will not change. The introduction of the new nexus does change the top k set for only gateway 3. Due to this, gateway 3 disconnects from one nexus and reconnects to the new nexus. The newly added nexus only moved connections from one gateway and not all. Now let us look at the reverse scenario where a nexus goes away. In this case, the nexus that went away was in the top set for both gateway 2 and gateway 3. Both the affected gateways picked the nexus with the next highest weight to connect to. The other gateway remains unaffected. And so, with rendezvous hashing, we were able to solve our socket connection limit while still maintaining an even distribution of connections with minimal disruption upon fleet change. In the collocated world, gateways talk to a single nexus, and so there was no concept of heat. Now, however, we need to expect dynamic load balancing. To enable dynamic load balancing, the gateway periodically polls nexus for load balancing factor, which is used to make routing decisions. Say one nexus just restarted and has only 5 streams on it, while the other nexus have about 100 streams each. Let us then look at the state of stream distribution after a little time t has passed. Say we follow a naive solution where we only route to the lowest loaded nexus. The gateway in this case will route all traffic to only the middle nexus, overloading it quickly. Another naive solution is to have the gateway route traffic randomly on a round-robin fashion. In this case, the nexus with low load would almost never catch up with the others. And so, a commonly used solution is to pick 2 random nexuses and route to the lowest loaded one. In this example, when a gateway talks to 3 nexuses, 2/3 of all traffic goes to the lowest loaded nexus, while the remaining goes to the other 2. This helps lagging hosts catch up without getting overloaded. Putting it all together, the off-box architecture provided us with the ability to enable customer traffic isolation, provide more fault-tolerant systems, and gain the ability to dynamically load balance. The off-box architecture served our team really well for a while. New major improvements and changes in RTI allowed us to consider a full meshed architecture. Going back to the 5,000-foot view, we now have a new service called Blade Runner that replaced Nexus. Blade Runner is a streaming platform that enables RTI's customers to write JavaScript services where devices connect to their JavaScript handler via a persistent stream, and the handler then interacts with Facebook infra, including the publish-subscribe infrastructure to serve streaming traffic. Additionally, a new traffic proxy, which we shall call WarpGate, was created that enabled us to maintain a full mesh connection. Zooming in, we see that every WarpGate now connects to every Blade Runner in the region, hence the name full mesh architecture. Just the full mesh connection allowed for better load balancing since each warp gate has more blade runners to distribute traffic against. In addition to that, we were able to enable sticky routing and virtual isolation of customers. The idea behind sticky routing is simple. Let us say that we have a live video A. Each client can request a stream to live video A for constant updates that the client may then display to the viewer. Without stickiness, the two requests can be served by any two random blade runners where each blade runner will then independently subscribe to the key value store for updates. With stickiness, however, the streams are now sticky to a common blade runner that serves their requests. Let us also introduce live video B shown by the pink line. Due to stickiness, regardless of the warp gate processing the request, streams for live video B will be routed to a common blade runner. Here too, only one blade runner needs to subscribe to the key value store for updates instead of every single blade runner having to do so. Stickiness has provided a lot of wins since all similar requests are being served by just one blade runner host. With stickiness enabled, we were able to reduce the number of requests to our key value store by about 15 to 20%. We also observed about 5% memory savings and about 7 to 10% CPU savings on Blade Runner. This brings us to the question of how. Unlike the off-box scenario, we have a full mesh where every warp gate is already connected to every Blade Runner. What we need now is for each warp gate to route different streams to their respective Blade Runners in a consistent fashion. This too can be solved by rendezvous hashing. Let us look at a single stream that is interested in real-time data from a feed Fi. In our earlier live video example, live video A would be one feed and live video B would be a different feed of data. A request to a feed can land on any warp gate and we expect the same routing outcome. We will use rendezvous hashing to compute weights for each Blade Runner host by hashing the Blade Runner host identifier with the feed's identifier. As an example, we can see weights for feed 1 on the right. As part of rendezvous hashing, we will pick the Blade Runner with the highest weight, in this case, the Blade Runner with a weight of 81. So now if a stream requesting real-time data from the same feed lands on a different warp gate, the result is the same since the weights are the same for feed 1. Streams that care about a different data feed, F2, depicted in pink, would have different weights for each Blade Runner. This leads to F2 picking a different host to be sticky on. The promise of minimal disruption is still valid. When the second Blade Runner goes away, the top weight changes only for feed 2, and so only related streams must reconnect. When the second Blade Runner is available again, the top weight once again changes only for feed 2, which then reconnects its streams back to the second Blade Runner. In both these cases, we never saw streams to feed 1 change its Blade Runner since its top weight was unaffected. Putting it all together, we see that rendezvous hashing helps all warp gates route to the same destination with good distribution and minimal disruption. That was sticky routing. The next major win was virtual isolation. If you remember, the off-box architecture isolated hot customer traffic from the rest. However, with Blade Runner, we got a lot more new customers, each with their own quirks. The number of isolations needed to be increased, and managing a fleet for each was starting to become painful and costly. Prior to virtual isolations, every Blade Runner served every single customer's traffic. Since Blade Runner is a streaming platform, each of these customers have their custom handler being run on Blade Runner. In some sense, you can think of this as having different customers co-locating their handlers. In such a world, if say customer Lorem saw a spike in traffic, it would affect the performance of other customers on the same Blade Runner host. Also, without isolation, every customer has to share resources, which is not desirable. What we ideally want can be represented best by the image on this slide. We want each Blade Runner host to serve only an individual customer's handler without sharing resources. The varying sizes are just a representation of how much resource each customer's handler is consuming on that Blade Runner host. Now, to define a virtual pool. A virtual pool is then a collection of all hosts serving a specific customer. In this case, the virtual pool for Lorem would consist of Blade Runners 1 and 6. The routing logic then filters Blade Runners by the virtual pool and does even load balancing or sticky routing within that virtual pool. For instance, if a request was identified as a Lorem request, it would only consider routing to Blade Runners that have Lorem present on them. Virtual pools are great for a few different reasons. Virtual pools help handle the noisy neighbor problem, as the isolation prevents one customer from affecting another. Such isolation also makes resource attribution to each customer easier. Finally, virtual pools help avoid the maintenance cost of creating and managing real host pools. This also means that all virtual pools can have common spare capacity to grow into when needed. We shall now look at implementation details next. We will start with warp gate visibility. Let us consider a single Blade Runner host serving two customers as handlers. The full mesh connection means that every warp gate within the region is connected to that Blade Runner. The heat status the Blade Runner host then streamed to every warp gate looks something like this. The heat packet has a load balancing factor as well as a newly introduced heat status. This is at both the host level as well as at the handler level granularity. In this example, we can see that the customer Ipsum's handler has a load balancing factor of 35,000 and is currently marked as low utilization. The load balancing factor is used to make even load balancing decisions, and the heat status is used to determine when to resize a virtual pool. It is with this heat information that WarpGate is able to build a view of the entire world and consistently route regular and sticky streams within each virtual pool. Now that we know how WarpGate learns of existing handler distribution across Blade Runner, the question turns to virtual pool placement. Since our team deals with low latency, real-time traffic and need to quickly scale up the virtual pool of a customer when needed, we have WarpGate handle placement as well. The problem of virtual pool placement is very similar to the two previous problems we solved using rendezvous hashing. This time, however, we want to be consistent on the virtual pool itself. Hence, the weight of a Blade Runner is determined by hashing an identifier of the virtual pool along with that of the Blade Runner host. We then filter out hosts that we might not want to grow into. These could be Blade Runners with already the same customer handler or Blade Runners with other customer handlers that we don't wish to collocate with. Finally, we pick the highest weighted Blade Runner to grow the virtual pool into. For example, when we see Ipsum on Blade Runner 2 get hot, we want to see WarpGate scale up the Ipsum virtual pool. And so, we first compute the weights of each Blade Runner for virtual pool Ipsum. We then filter out the Blade Runners we don't want to grow into. Since Ipsum expects perfect isolation, we don't want to grow into a Blade Runner that already has another customer's handler on it. Finally, from the remaining Blade Runners, we pick the one with the highest weight and spin up Ipsum then. Our scaling up operation allows Ipsum traffic to balance onto this new host 2, hence reducing the hotness we initially saw in Blade Runner number 2. Let us now look at a scaled down example. Here we see that Ipsum on Blade Runner number 2 and 4 are underutilized, triggering a decision to scale down. Since we ignore hosts that don't have the desired virtual pool, we end up with this simplified view. We use rendezvous hashing again to compute the weights. Since Blade Runner B has the lowest weight, all warp-gates will request that Blade Runner host to stop serving Ipsum. Once scale down is complete, we notice that Blade Runner B is no longer serving Ipsum. The traffic served by Blade Runner B is now served by other Ipsum Blade Runner, better utilizing resources. It is worth noting that we picked the lowest weight here. This is done deliberately since it makes the scale up and scale down function like a stack, with the most recently scaled up Blade Runner to be the first to see scale down. To illustrate virtual pools in actions, let me share a graph from a very popular live event late October that garnered a lot of real-time traffic. This live traffic was served for a customer I shall call Lorem. In this diagram, we see that the total streams handled by Lorem more than doubles before it comes back to a more normal range as seen in green. To handle the spike, we can see that the number of Blade Runner hosts serving Lorem, seen in blue, scale up proportionally in an extremely short span of time. All of this took place without adversely affecting any other Blade Runner customer, and the entire thing was completely automated with no need for any in-person intervention. In summary, we can see that virtual pools have allowed us to deal with the noisy neighbor problem, have better resource attribution per customer, and reduced maintenance costs. Putting everything together, if there are a few things I'd like folks to take away from this presentation, it would be 1, moving away from colocation. There are many cases where colocation might make sense. However, co-locating services does come with a fair share of problems, and removing co-location is one good way to tackle these problems while also opening up the opportunity for traffic isolation, higher fault tolerance, and dynamic load balancing. Secondly, rendezvous hashing. It is great for when each client has to independently make a decision and we still expect to see an even distribution with minimal disruption. I hope the various examples in this presentation helped give you a good idea of all the different scenarios where it can be used. Finally, full mesh architecture. Through full mesh architecture, our team was able to unlock massive savings thanks to the ability to route traffic in a sticky fashion. The full mesh architecture also enables us to create and manage virtual pools that reduce maintenance costs, help with resource attribution, and isolate noisy customers from one another. While a full mesh architecture might not work everywhere due to various constraints, it is definitely a great value add wherever possible. Thank you very much for your time. I hope you found this presentation useful and had as much fun as I did putting it together.